Okay, this is the review for the final midterm, or the final exam, I guess. Same format as before, 8 to 8:30, Monday, Wednesday, Friday, but this time it's on the Friday of week 14 and the Monday and Tuesday of week 15, the last week of classes. So don't forget the slightly rearranged schedule. It's on the syllabus, so you should see that. Again, if you have a crisis, then just send in a time-stamped photo of your work immediately so that I get it, and we'll take care of it. For this one, it's not a comprehensive exam, but the material recovered is on pipes and networks, the last class of week 11, on external flows, which is week 12, and then open channel flows, which is week 13, but also with the energy equation for week 8 thrown in there as well. So that's kind of implicit in all of these anyway, a kind of fundamental component. 3 questions. Again, remember, it's Friday, Monday, and Wednesday, not Monday, Wednesday, Friday. The first question's on pipe networks and includes the energy equation. Second question's on external flows, and the third question is on open channel flows, and specifically uniform flows. So that makes it a bit more straightforward maybe for you. The energy equation we saw in week 8, it's really Bernoulli equation. Remember that it's written from upstream to downstream always. It has a pump head included on the upstream portion, and it includes both major and minor head losses on the downstream side. Major losses are in pipes, given by a friction factor, length of pipe, diameter of the pipe, and the velocity in the pipe, recall. And in fittings, the loss coefficient multiplied by the velocity in the fittings. These are summations, so if you have multiple pipes or multiple fittings, you have to add them together. And the pump head term is defined in terms of the power in watts, joules per second, or newton meters per second, gravity, and the mass flow rate. And the mass flow rate, of course, is the volumetric flow rate times density. So the energy equation is fundamental to kind of all of our pipe flow calculations. We've drawn the parallel between pipe flow and external flows, and it's on the Moody chart for pipe flows, and it's on the coefficient of drag or coefficient of lift charts for external flows, but they're basically the same. They have the same format. They're scaled relative to Reynolds number. Reynolds number is defined in the usual way as a velocity, density of the fluid, and the diameter. For a non-circular section, it's hydraulic diameter, which is 4 times the area of flow divided by the perimeter, and the viscosity of the flow. More significantly, they divide into both laminar and turbulent flows around a Reynolds number of about 2000. And the main important thing for these is that the friction factor is a function of Reynolds number, and therefore viscosity in the portion where it's laminar. So it changes with Reynolds number, but it's independent of the relative roughness. And in turbulent flow, it's the opposite. The friction factor is independent of Reynolds number. It doesn't change with Reynolds number, but it does vary as a function of the relative roughness of the flow. And so they're fundamentally different. And this comes out in the fact that the solution for solving the equation means that once you substitute Reynolds number into the friction factor, you get a velocity out of it. And once you do that for turbulent flow, you get a velocity squared term that you have to square root. So this applies both for external flows and pipe flows, the same kind of behaviors. We have 3 classes of pipe flows where velocities are given or flow rates are given, which are definitely the easiest to solve. And we have class 2 problems where you have to solve for velocity, or class 3 problems where you have to solve for geometry. And the questions in this, I think, are in terms of class 1, as I recall. But anyway, you know how to solve all 3 of them. The solution procedure is to assume a velocity and calculate a Reynolds number. From that Reynolds number, get a friction factor. Check from the head loss equation what the velocity is, and then recalculate what the Reynolds number, recheck the friction factor, and so on. So that's kind of the closed circuit in evaluating that. For non-circular pipes, the hydraulic diameter is given by 4 times the cross-sectional area of flow divided by the perimeter of flow, and that could be used in the Reynolds number equation to get Reynolds number. Notably, if you talk about open channel flows, the hydraulic radius is not 2 times the Reynolds number. And so this is not the case, so beware of that. So anyway, take care, make sure you don't use this ratio, that it's 4 times the hydraulic radius, just from this equation here. For pipe networks, you know that when the pipe networks are in parallel, then the flow rates is just the sum of the flow rates of the individual flows, and the head losses have to be the same across both pipes because they're both ending up in the same big tank. For series flow, as you go from 1 to 2 to 3, the flow rates have to be the same because of continuity, and therefore if that's the case, then the head losses on each of these individual components have to be cumulative to get the final total head loss across the system. And for branched pipelines, then you know that when you look at the head drop on the first pipe, it has to be the same head drop going down on pipe 1 to this point, and therefore if it's ending up in a large tank in the downstream side, the head losses on pipes 2 and 3 have to be equivalent to each other because they're all ending up at the same big tank with the same elevation, and you should use that expression to define those. Okay, so I guess we didn't really say much about this, but it's the same as the Moody chart. You have either laminar or turbulent flow. It breaks around 2000 for these. For laminar flow, the coefficient of drag for a sphere is 24 over the Reynolds number. It changes for different components, for a cylinder or a sphere, but it's proportional to 1 over the Reynolds number. And so if you know what the Reynolds number is, you can get the coefficient of drag directly from doing that or from using the equation. And for turbulent flow, flows above 2000, then the friction factor or coefficient of drag or coefficient of lift are constant largely, except for some variations in that. And this allows you to write the coefficient of drag as a function of the drag force or lift force divided by a half density velocity squared times the cross-sectional area of the object. And this cross-sectional area of the object is usually the facing area of flow. For a sphere it doesn't matter because it's the same in all directions, but for a cylinder it might be different depending on the direction at which the flow impinges on the structure. And usually from this you want to be able to calculate the coefficient, the drag force as a function of the velocity, which is known if you know the Reynolds number from this chart here. And so the calculation sequence really is to use Newton's second law, F equals ma. Usually the accelerations are 0, and we can write this as equal to 0. So the sum of forces just sum to 0. And so that means that on the laminar side of flow, the coefficient of drag is a function only the Reynolds number, not of anything else. And therefore, if we substitute the Reynolds number into this Euler equation, substitute the coefficient of drag into this equation, we end up in an equation which is proportional to the velocity to the power 1, and it varies only with viscosity in this. And if we're in the turbulent regime, if we substitute the coefficient of drag into this, we get a magnitude of the drag force, which is a function of the velocity of the power squared, power 2. And so you solve them fundamentally differently, whether it's laminar flow or turbulent flow. And we've done examples to deal with both of those. Usually, if you calculate the magnitude of the drag force, if you know what the flow velocity is, this of course results from the fact that you have flow around the cylinder in some form. There are 2 components to the forces acting upwards. There's certainly a drag force if you're looking at this, but maybe if the fluid is liquid rather than a gas, then the buoyant force is significant because the magnitude of the unit weight of the specific weight of the fluid is large in the case of water. In the case of a gas, it's not so large at all, and probably you can neglect it. But if it's a fluid, then perhaps you can't. And you just sum the forces acting vertically, which would be the buoyant force and the drag, the weight, which is dragging it down. And so by applying Newton's second law, you balance forces to find out what the net force is. If it's not accelerating, then they have to balance each other. If they balance each other, then if you've substituted for the drag force as a function of a velocity, then you can solve for a velocity. And importantly, the velocity comes out of the system. If it's turbulent, then you'll end up with a velocity squared term from using the Euler equation. If it's a laminar flow, then you'll end up with a velocity to the power 1 term to solve, but you can solve for the velocity nonetheless. If you know what the drag forces are, if you have a combined structure, a composite structure, you can look at the drag forces on different components, and you can sum either the forces or the moments if you want to be able to define behavior relative to some lever arm, and you can solve for those directly. And that is external flows. So finally, for channel flows, it's a uniform flow question, so this is really all you need. The flow is defined in terms of an average velocity of the flow, which is uniform across the channel. The channel has a depth, which is given by y. It has a width, which is given by w. The flow per unit width is given by lowercase q. Or if you need to calculate the total flow, volumetric flow rate, it's just the product of the average flow rate times the cross-sectional area of flow. Cross-sectional area of flow is just the width times the depth, which is relatively straightforward to get. If you want to calculate the hydraulic radius, it's equal to the perimeter. The perimeter is just this green line because the top doesn't matter, the wetted perimeter, and the cross-sectional area is the width times the depth, and so the hydraulic radius is just width times depth divided by the wetted perimeter. The Reynolds number, if you need to calculate it, is defined not in terms of the hydraulic radius here, but it's in terms of the hydraulic diameter. And we know that the hydraulic diameter is equal to 4 times the hydraulic radius, just from the equations that we have, so you need to be careful with that. And as a result of that, you can use for uniform flows anyway, where the flow velocity is taken as the same magnitude across the channel. The assumption is that it's turbulent flow. And then the mean flow velocity is given by a coefficient, which for SI units k is equal to 1, kappa. The Manning coefficient, which depends on the roughness of the channel. The hydraulic radius, which you know how to calculate from what we've defined up here. And the slope of the bed of the channel. So the float doesn't slope, but the bed slopes at the base here. So the bed slope along a base, this would be equal to the drop. The bed slope is equal to the drop divided by the length over which it occurs. And so this is the slope that we use in this particular case. So this is just equal to d over L. And if you have a mean velocity, you can calculate the volumetric flow just by multiplying the mean velocity multiplied by the cross-sectional area. So that's pretty straightforward. And we don't have a question on this, so I won't mention that. And so you can avoid figuring out exactly what the gradually varying flows are. So that's about it. So those are the components that are on the question. Remember, it's on a Friday, Monday, and Tuesday rather than our normal format. This is because of the requirement that you shouldn't have anything in your final week which is worth more than 10% of the grade. And so we juggle things that way. And good luck.